In the previous video, we derived a formula which gives the frequency of a standing wave pattern on a stretched string in terms of the number of bumps in the pattern, the length of the pattern, the tension in the string, and the linear mass density of the string. In this video, we're going to use this formula in a straightforward example problem. This example is based on a demonstration which I've done many times in my in-person classes. So we take a string, and one end of the string is connected to a vibrator. So the vibrator just shakes the string up and down a fixed number of times per second. And then the other end of the string goes over a pulley and is connected down to a fixed mass. We measure the length of the string, and we know the linear mass density of the string. And the question is, what mass should we hang from the end of the string in order to get some predetermined number of bumps to show up in the standing wave pattern? So here I've given that the vibrator frequency is 120 cycles per second, which is the same as the actual vibrators we use in the demo in class. We're going to say that the length of the vibrating portion of the string is 108 centimeters. We'll say that the linear mass density is 4.31 times 10 to the minus 3 grams per centimeter. Then the question would be, what mass should we hang from the end of the string to get the standing wave pattern, which is shown in the figure? First, let's look at the figure, because the figure tells us how many bumps are in the standing wave pattern. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9 bumps in the standing wave pattern. So we're going to take n equals 9. So now we have pretty much everything we need. We just need to take this formula from the previous video and apply it to the problem at hand. So the formula from the previous video says that the frequency of an n-bump pattern on a standing wave is number of bumps divided by twice the length of the pattern, then times the square root of the tension divided by the linear mass density. In this experiment, the tension in the string is whatever is needed to support this mass, which is hanging at the end. So what I'm going to do is go into the formula here and replace the tension with the weight of that hanging mass, namely capital M times little g. Then we divide by the linear mass density. So all we have to do here is solve for the mass and then substitute in everything else. To start, I'm going to just square both sides. So I now have frequency squared equals n squared over 4l squared, then times mass times little g divided by linear mass density. To isolate the mass, I'm going to just move everything else to the other side and then flip sides. So that will give me mass equals 4l squared, linear mass density, frequency squared over n squared g. So now let's make our substitutions. First, we have the number 4. Let's put in the length now. I'm going to be working in CGS, so I'm putting in the length as 108 centimeters. That is squared. Linear mass density, 4.31 times 10 to the minus 3 grams per centimeter. Then the frequency would be 120 cycles per second. So I'm putting in 120 seconds to the minus 1 squared. N is the number of bumps. In this problem, we have n equals 9, so n squared would be 81. And then g is 980 centimeters per second squared. First, let's make sure that the unit of all of this comes out to be an appropriate unit per mass. So I'm going to come down here and just look at the units in the numerator first. We would have centimeters squared times grams per centimeter times 1 over second squared here. Divide all of that by centimeters per second squared. All right, so numerator and denominator both have 1 over second squared. That cancels. In the numerator, I have centimeters squared over centimeters, which is just centimeters. In the denominator, I have centimeters. So all of those centimeters cancel, leaving me with just grams. So the unit of the answer is going to be grams, which is appropriate for a mass. Now, how many grams? Let's just put all of this in the calculator. So putting all of this into my calculator, I get 36.5, and then the unit is grams. So now we have done an example problem involving a standing wave on a stretched string.